Okay, just going to do a video on the preamps and the way I'm buffering them and interfacing them to the ADC, or the multi-channel ADC, and the issues that I'm finding with that. So first of all, let's have a look at the PGA 2500s. Let's have a look at the output voltage range. So we have, no matter what gain, audio gain, we have differential output on the PGA 2500s of 8 volts peak to peak. Well, it's going to be slightly under that. Slightly over 8.1 volts. We're running on VA plus 5 volts, VA minus 5 volts, the power rails, and the data sheet basically says VA minus plus 0.9, which is 4.1 volts, and then 4.1 on the plus rail minus, so it's 8.2 volts peak to peak. That's the maximum output. Okay, so I need to get, well, the idea is that I get that into the CS5368 inputs, and so we take a look at what the ADC requires on its inputs, and we're powering the CS5368 on 5 volts analog, and so it requires 5 volts times 1.13, which is 5.65 volts peak to peak on the on its inputs. So we need to attenuate the inputs from 8.2 volts down to 5.65 volts peak to peak, which is, I guess, around 2/3 or something. First of all, let's look at the recommended filter on the buffer, which the ADC recommends. And the first thing you notice maybe is, if you know about op amps, I had to do a bit of research on this, but first thing you probably notice is that the audio signals are going into the non-inverting inputs. The filter is RC, based around this RC here in the negative return loop on the inverting side of the preamps. Okay, so I can't really attenuate with these op amps if I'm using this filter in this way, with this setup, since the non-inverting inputs have a minimum gain of 1, and we're looking for 0.75 or something like that to knock down the PGA 2500 differential outputs from maximum voltage peak to peak of 8.2 to down to 5.65 peak to peak. Alright, so with the help of someone else suggested I use the sorry, I'm not used to this. Use the inverting inputs and flip the phase digitally after it's gone into the ADC. In fact, the ADC will flip the phase. I'm not sure if I can find that simply. It will be in the register, I think, somewhere, that inverse phase in the ADC, or if not, I can do it in the DSP. digitally. So the fact that it's inverting is not an issue. Now also I need to bias the incoming voltage swing around 2.6 volts. In actual fact, I'm going to do this with VQ from the ADC on pin 7. VQ is like VCOM, and it outputs 2.6 volts around. It should be half VA, but it's not, and it varies depending on the temperature of the device and so forth. So I mean, as you see here, you know, it says half VA, but actually it's kind of real world it's not, and the closer to, you know, what's on VQ, the better for distortion and so forth, I think. Now the VQ pin only puts out 10 microamps, which is nothing, so you need to buffer it, and you need a low noise buffer, otherwise the noise can transfer from whatever into your audios directly into your signal. So I'm using opa143. In fact, I'm using opa2143 because I have a DAC that has the same requirement, needs to have a buffer from its VQ as well, sent to the line drivers, but that's another story. Okay, and right, so here's the PJ 2500. It's just kind of pretty standard setup, and then the signal comes in here, and where's VQ? And this, do I have the right one here? I hope so. Because ground. Oh yeah, sorry. Here is VQ coming in through some 10Ks. I'm not quite sure. Yes. Now it's not very clear in this diagram, but the non-inverting inputs do need to go to ground, and you have to put them through a capacitor. I'm not sure of what these values should really be. I think 1 NF's enough, but it may need to be 1 UF. I'm not sure. It may not matter. I need to work on that more, find out more, read some more theory on that. But I'm presuming the non-inverting inputs need to see ground, the AC, but obviously the VQ can't look at ground. It can't connect to ground, because otherwise it would just be 0. Or you wouldn't have anything there to bias the inputs with. Now the ADC requires that, it swings around 2.6 volts ish. Okay, right. So then we need to attenuate. Now we can attenuate once it's in inverting mode. The buffer op amp. So that's where we go to. I'm using Pspice for TI, which is a free Pspice app from TI. I'm sure the real thing by OrCAD is much better, but this is free, and I don't have $7,000 for simulation software. Okay, so I'm supplying the 8 volts. Let's call it 8.2 to be for the amplitude. It shouldn't really say DC there, I don't think, but I'm not actually using this one. It's the volts amplitude that you need on this AC, just for simulation of the peak voltage, the maximum peak input AC voltage across its the two op amps. So really what I need to do is calculate calculate the gain between R1 and R2, although the filter, the RC filter here, which is the 50 kilohertz cutoff it's a recommended thing for the ADC, just to filter out any extremely high noise which might have harmonics and affect your audio and so forth. There's more to it than that, but anyway, transients, God knows, I don't know. But for this, the purpose of this, we just need to add the 91 ohms and the 634 ohms to make 725 ohms, I think. Because because the gain is simply a division of R2 by R1. So in this case, if we've got 725 ohms here, wait, let's just do this calculation quickly. Calc. So okay, we've got 725. Let's divide it by 1. Oh no, we don't. So 725 ohms divided by 1,400 ohms, and you know we got near enough, you know, half the gain, you know, 0.5 gain. So you know our 8.2 volts should be cut down to 4.1 volts max amplitude on the outputs between these, you know, out and out of both the two preamps. opa1602 is a dual preamp, yeah, dual op amp. So here's our probes. Let's run that, and then we should get some kind of graph. Let's just get rid of it. Alright, now this is exactly why I needed to model this. Is here you can see some pretty bad clipping at 4.2 volts or so. Now we're okay on the negative side. You can see at 2.6 volts, it's not very good scale here, but you know, assuming this is 2.6, this is where we added our bias. So you know we biased here, and so our volt, you know, our both our hot and cold balanced audio is swinging around 2.6 volts. So we need to get rid of the clipping. So really we need to attenuate more. It's the only thing we can do. And the reason it's clipping is that we're running these op amps at +5, -5 power rails, just like we are on the, you know, we're using the same power rails as the PGA 2500s, because you know they're on cards and they slot into the back plane, and running, you know, you can run the opa1602 right up to 30 volts plus minus, I think, or anyway at least 15 plus minus. But you know, running those extra dual power rails, I don't know, perhaps more noise, more rails, more pins, you know, just kind of ugly really. So I'm trying to avoid that. So is just make sure we've got 8.2 coming in. So you know, the thing really is just to kind of is to increase the decrease the gain, increase the attenuation until we can remove the clipping really. Now, and also we're using absolute maximum peak to peaks here, and probably wouldn't see that in real world unless you're kind of overloading the preamps anyway. But it's, you know, obviously you have to design it to be safe. So what have we got now? Let's have a look. No, still clipping. Zoom in, get a better picture of that. Yeah, we're clipping at the same place, so we need more attenuation. And I can't move the bias point because obviously the preamp, the ADC requires that. That's the bullet train. I'm in Japan, so that was just the bullet train going past. I don't know if you heard that. On the edge of the city here, and it does. It's probably already doing 200 kilometers an hour. So let's make that say 1.8. I can do, you can do the maths between this ratio between 8.2 volts and your desired 5.2 volts peak to peak. But I'm just playing around, showing you the software as much as anything. So let's go 1.8. And you can do the maths. It's just it's 725 ohms divided by 1,800. Well, let's do it. Let's so I'm not great at calculations in my head. So 725 divided by 1,800 ohms is so it's 0.4 gain, pretty much, bang on. And run that simulation. That takes a little while. All right, so let's just zoom in that. Okay, so that looks pretty, there's no clipping there. I probably could pull it back to 1.7 or, I can't adjust the, well, perhaps I can, but I don't know any way of adjusting these values to change the filter design. And I'm not, until I run, then I'd need to look at the dB filter simulation to make sure these are still doing the right cutoff corner frequency at 50 kilohertz low pass. There I do have it set up so if I make this these probe settings active, it's AC sweep noise between let's just get rid of that noise between the start frequency 20 hertz to 200 kilohertz. I just went over anything way up high, 250 points per decade. So if I for instance if I take this advanced probe dB magnitude, sorry, let's just look at exactly what this is. Let's take these off. Right, I think you can leave those, so they just be ignored. So if we look at markers, dB magnitude of voltage, so it's the magnitude of voltage in dB. Let's have a look at that. I think you can put them on, I've already got one there. Okay, now assuming if I run this might not work because you do have to really get, yes, I think that works. Now this is the dB the amplitude of the voltage in dB, I assume. So sure, yeah, this is around 50 kilohertz, and then we're starting to drop off. So we're losing. Yeah, this could be steeper, I think. So it could well be. I'm not really sure why the blue one is lower. And I need more investigation on this in terms of understanding of this. This is obviously log, logarithmic or not, or linear. Yeah, so with dB you generally look at it in log, I assume. And with the kilohertz range, I guess you would look at it in log too. So yeah, I'm not really convinced. I might need to play around with these filter values. After changing R1 relationship with R2, does this, and changing because this, demonstration, this example filter in the data sheet assumes it assumes, you know, what input voltage is it assuming? And maybe since I attenuated, you know, under the maximum swing, maybe these values need changing fractionally to kind of make that filter harsher, or I don't know. And you know, going back quickly before I finish this is really taking forever, sorry. Let's make that one active. I think that's all I do. Let's just try and run that again. Just wanted to check what final output swing we have at. Okay, so if that is 1.5 volts there, what's that, 200 millivolts? So within, let's just say it swings up to 4 volts, take off a volt. So we got, you know, kind of 3 volts point to peak swing going on, you know, which is, and that's centered around 2.6 volts. So that would work pretty well. And I can probably squeeze, I could probably squeeze, you know, a little bit more in there. We've still got, actually, I think we were getting clipping at 4.2 volts. So I've got, you know, 200 millivolts to kind of play with. Probably leave 100 millivolts. And there's plenty of room at the bottom, and then the negative down at the 1 volt range. So it's really just the top, you know, the headroom, and obviously the opa1602 requires, you know, it probably requires 900 or 800 millivolts something. It's probably not rail to rail as such. And then, you know, and how good is this model? It probably is way better than my knowledge, but yeah, I don't know. Okay, that's pretty much it. Let me know if anyone knows, wants to leave a message on the Hackaday or on the YouTube video of this filter, and perhaps that you know more about the, you know, modeling in dB. If I'm doing something wrong here, I'll just show you the settings I've got. I've got the analysis set to AC sweep and noise. You know, maybe you change the points, but I mean that's just the amount of sampling points, I assume, of the thing. Let's just run that one more time. All right, where is it? Here. That looks slightly better this time on the, oh, that's odd.